Hello and welcome to, I admit it's kind of a major presentation on energy here. So previously we talked about work and power and how to calculate the work done by a single force. And we calculate work that way in order to calculate the energy and keep track of the energy. So now let's explore that topic, which is of course probably the most central topic in all of science. So here's the thing, and the problem is there's no really satisfactory definition of energy. I mean, the most common thing is people will say, "Oh, it's the ability to do work." But I mean, that's not a very satisfying answer because of course we define work in terms of the change in energy, so it's kind of a circular thing. The best kind of thing I can say about it is it's about a relationship between objects and the ability in that relationship to affect change, to affect physical change, right? So if you have more energy than you did before, you can change things about your environment more than you could before. And it's not really necessarily a property of an object, although we associate the energy of something, but really it's always an energy in relationship to something else, right? So it's a relative value, kind of like what we talked about with velocity, right? There is no absolute speed in the universe. There's only relative velocities, right? And so energy is kind of like that also, right? So it's not a thing of its own, and you shouldn't really picture it of like a goo or something. Even though we're going to use lots of metaphors and to track it and stuff, it's really quite an abstract concept. But it is the rule of the game, right? It is the most important law of nature that we've ever discovered, I would say. So let's talk about this idea of conservation of energy. Why? I would make the argument that energy being conserved is actually what drives Newton's third law, but I think Newton's third law is something that we're already comfortable with in this class. So let's start there. So think about the work being done in this picture, right? You've got the hammer that's coming in and it pushes the nail, right? It displaces the nail to the right, and there's a force to the right, and so therefore there is positive work being done to the nail by the hammer, right? It's positive because the displacement vector and the force vector are in the same direction. Now, we also know by Newton's third law that there is an equal and opposite force on the hammer from the nail. So let's think about the work done by the by the nail to the hammer. Most people wouldn't think about that, but there is a force applied while the hammer is displacing, right? The hammer is clearly displacing to the right as it forces and drives the nail to the right, yet it is experiencing a force to the left. So therefore it is a negative amount of work, right? Because it's going to take the cosine of 180 degrees when you calculate the work done by this force on to the hammer. Now, the displacement's the same and the forces have the same magnitude. The only thing that's different is the sign, right? You got positive work being done by the nail and an exact same amount of work with a negative sign in front of it being done to the hammer. And so there was energy exchange between the hammer and the nail, but the total, right? The total in this picture is the same before and after the strike. And this really kind of, I'm talking about this to motivate this idea of conservation energy, right? If you were to draw a box around the hammer and the nail, the number of joules, which is the unit of energy, is the same before and after. And that's what it means for things to be conserved in a science sense, right? It's the same before and after. You can transfer it from one object to another within the system, or you can transform it from one type of energy into another, but the total is the same, right? Now, there are, excuse me, three different types of energies, right? So these energies could, in the system, could be found in one of these three different forms, right? Kinetic, which is the easiest to understand, right? So that is related to motion, right? If you give something kinetic energy, it's going to be going faster. If you take kinetic energy away from it, it's going to be going slower. Then there is potential energy, which can be stored in a system. Doesn't belong to a single object, but rather it is in between the two objects that are exchanging forces. Remember, every force is an interaction between two objects. So if you hold a book a few feet above the ground, right, there's some potential energy, some gravitational potential energy there between the book and the planet Earth. And then there's internal energy, which is just kind of us being sloppy, right? What's really going on when we talk about heat and temperature is we're just talking about microscopic kinetic and potential energy. That is the kinetic energies. You should know this, right, from chemistry, that the kinetic energy of the individual molecules is what we call temperature, right? So when something gets hotter or colder, what we're really saying is that the average kinetic energy of those individual molecules is going down or up, right? So Instead of actually tracking all of those energies as kinetic energy of the system, since they're microscopic and we don't really care about the details, we just lump them all together and talk about them as internal energies. And that's generally where we're talking about heat transfer and temperature and things like that, changes of phase. Because energy is so important and used in basically every aspect of science and engineering, there are a ton of different units, right? So I'll just introduce you to maybe the most common one. The most important one, of course, is the metric standard unit, which is defined in terms of the work done, right? So that's a joule. A joule is a Newton meter. We already covered that when we talked about work. The second most common one that you'll see is calories. Calories came from measuring the energy of heat transfer, right? That's the energy it takes to warm up 1 gram of water, 1 degree Celsius. So that's about 4.18 joules. Then there's calories with a capital C, or food calories, or sometimes they don't even indicate it in any way. But the nutrition industry uses these kilocalories, right? So they're actually 1,000 calories. And I hardly ever see them actually indicate that properly with the little k, but you're just supposed to know, if you capitalize the C or call it a food calorie or something like that. Kilowatt hours, that's the unit of energy that the electric company will bill your household for the amount of energy you pull off the grid in a given month. So that's a weird kind of unit, but if you work it out, kilo is 1,000 and a watt is a joule per second, an hour is 3,600 seconds. That works out to be 3.6 megajoules, which I think is why they don't bill you in joules, right? There's another old thermal unit called a BTU, a British thermal unit. That was based on a lot of work done with engines and things like that. And that's 1,055 joules. And then when you're talking about really small amounts of energies, like the amount of energy for an electron to be ripped off of its atom, to ionize the atom, or for an electron to jump between orbitals, instead of talking about the microscopic amount of energy you need to do that, they talk about it in a practical sense. When you are moving a single electron around, you're usually doing that with electricity, and so you're doing that with a voltage differential, which is something we'll talk about when we get to electricity. But anyway, this electron volt is actually a unit of energy, 1.6 times 10 to the minus 19th joules. Okay, we're going to stick with joules, though, right? Now, the systems are, when they're not isolated, right, that means the energy can leak out or come in. And there are all these different ways. I have a picture here for you. So, within the system, you can have your joules of energy in any of these 3 boxes, if you will, 3 pockets, kinetic, potential, or internal. And then these are various ways that energy can be taken in or out of the system. If you go in there and just remove some mass, right? If you send some electrical power in or take some out, if light is shining in or light is coming out, right? Not just visible light, but the entire electromagnetic spectrum. Heat, of course, can be transferred in or out by any of the heat transfer methods. Sound, of course, carries energy with it. And then the one we're going to be mostly concerned with, which is how you physically are doing it, because that's what we're talking about in the class right now, is like, applying forces to do things, work, right? So we're going to concentrate on the work methodology of moving energy in and out of the system. But if none of those things are happening, right? If the system, if the what you've drawn a box around doesn't have any of that happening along the edges, it can be happening internally between objects within your system all day long, but the total number of joules will be the same before and after, right? So this is the idea of conservation energy. It's not that the kinetic energy is conserved by itself, or the potential, or the internal energy, aka thermal energies. It's that the total is the same. So let's think about the work done by a single force, though, because that's the way we're going to really focus on transferring our energy. The work done by a single force could actually be taking energy into or out of any of those 3 pockets. So let's look at this a specific example to walk through this. All right, so I'm going to push this crate up this incline, and so it's displacing up and to the left with that blue arrow. And there's some friction there, and of course there's the normal force, and there's the gravity. So let's go through each one of the forces, right? My push is in the direction of the displacement, right? And so I am pushing it in the direction of displacement. That's some positive work. So that, of course, is going into the energy of motion. Some of those joules are going into the energy of motion of the system because it wasn't moving before, and now it is moving as a result of my push. The friction force is 180 degrees, is exactly opposite. So it's doing negative work, right? The displacement is up and the friction is down. So it's taking some joules out of that kinetic energy, right? It's slowing you down. And where does it put it though? It puts it into internal energies on the plane itself or the bottom surface of the crate. The normal force is perpendicular to the push, so it can't claim any responsibility for that displacement, and so the work done there is zero, right? Formally, because you're taking the cosine 90 degrees. And then gravity here is larger. The angle between gravity and the displacement is larger than 90 degrees. So when you take the cosine of that, it is negative. So it is working against the displacement. And so it is doing negative work, right? So it also is taking joules out of the kinetic energy that I was trying to put into it with the push. And where does it put those joules of energy? Well, it doesn't go into kinetic energy anywhere, and it doesn't go to thermal energy. It actually goes into potential energy, right? And we're going to talk a lot more about potential energy. Super important concept. But here's in one kind of simple everyday problem, you can see all three forms of energy are involved. So like I was saying, the most straightforward one is the kinetic energy. So here's the formula for kinetic energy. If you have an object with a mass m and it's traveling at velocity v, you square it, so you lose the directional information. So you could really think of that as speed, 1/2 mass speed squared, right? Because a velocity vector squared is like a dot product of the velocity vector with itself. So 1/2 mv squared gives you the kinetic energy of the object, right? And this is a relative term because velocity itself is a relative term, right? So however you decided to measure the velocity, whatever point you decide to measure the velocity relative to, that's the point you're measuring the kinetic energy relative to, right? Now there is another form of energy, kinetic energy, and that is another way you can have motion is to have rotational motion, right? And so it has its own formula that looks very similar and kind of follows a similar idea, but we're not going to pursue rotating objects in the course at this time. So if you take, and this is the simplest version of the work energy theorem, right? And students always just want to live right here. And if you can solve the problem this way, that's great. Then you don't have to mess with potential energy or thermal energy. But if you have a problem where you can determine the net work, that is the work done by every single force, sum it all up, right? Like in that previous problem, you just find out the positive number of joules of work done by the forces doing positive work, and then subtract out the other ones. You'll get a total number of joules that are given to the system. And so whenever you find that total work done by every single force, don't ignore or discriminate against any forces. That will show up in kinetic energy, right? So if you've got positive overall work, the object will speed up and you'll get some increase in kinetic energy. And if the overall work done is negative, then it's going to be slowing down and you'll get some negative change in kinetic energy, right? So this is kind of like the F net equals ma of the work energy theorem. Now, that, of course, is no coincidence because that is actually where the 1/2 mv squared comes from, right? So the 1/2 mv squared comes from sort of derived, starting with Newton's second law, take the F and the A and to make each one have a dot product with displacement, and then go through the formulas of kinematics, and that's actually where you get the 1/2 mv squared term from. It comes from F equals ma. So if you like, this is like the circular algebraic definition of work and energy. Far more interesting though, and you can only actually apply and use and see the beauty of conservation energy if you open your mind to potential energy, right? So let's back up. Before we talk about potential energy, let's talk about the work done by forces, right? And so the work done by forces actually can be divided into two camps. There are forces that when they do work, the work they do is completely path independent. It means it doesn't matter how you go from A to B. You're always going to get the same amount of work done. In this case, I guess it would be from A to E, right? So if you're lifting something, say from the ground at point A on the left-hand side, and you want to put it on the top of a shelf or something like that at point E, it doesn't really matter which of these paths you take to get there. The work done by gravity specifically, not the work done by you, but the work done by gravity will always wind up being the same. And that's because of the dot product, right? The dot product is going to eliminate any sort of x motions that you have, right? Because gravity is always pointed in the negative y direction. And if you overshoot, like if you go all the way up there to point D and you do, gravity has done too much negative work, because overall gravity is doing negative work, right? Because you're displacing upward and the force of gravity is downward. That will be canceled out when you bring it back down to the right height when you go down from D to E, right? So if you overshoot or undershoot, eventually, as long as you wind up in the same place, the delta y's will all have to cancel out. And it doesn't matter what you do delta xy's because the dot product gets rid of it, right? So our very smart way of defining work gives us certain functions, certain forces, not all forces, have this state function associated with them, which is the state function is a really fancy way of saying it's path independent, right? All you need to know are the endpoints, and you can calculate the work done by those forces. Your average everyday force is not like that, right? Like if you were pushing or pulling on something, like the work done by you is going to be very path dependent. The work done by friction, of course, is path dependent. But there are a few, and they tend to be the universal fundamental forces, right? So gravity, the elastic materials, if they're obeying Hooke's law, will do that. And electric forces, which we haven't talked about yet, right? So those are the big three conservative forces that have potential energies associated with them. So what's the point in thinking about that? The reason why those forces are path independent, the conservative forces don't care about the path, is because they're actually taking the joules from or into the potential energy that they have stored in the system. So, for instance, if you lift a rock from the ground, right, in the previous example, let's pretend like that was a rock we were lifting, then when gravity's doing all that negative work, it's taking energy away from the rock, right? That's what it means to do negative work. As you lift it up, it's displacing upwards, right? And gravity is always downwards. And then where do those joules go? And the answer is they go into the bond between planet Earth and the rock. They're in the relationship right there. And it's stored there and it's readily available. As you know, if you drop the rock, right, lift the rock up 2 feet, drop it 2 feet, you get the energy that gravity took out of it right away, which is very different than the energy you put into it, right? You don't get the energy you put. If you push, the couch across the room and you do all these joules of work to the couch and then you let go, you don't, they're not available to you, right? The couch doesn't spontaneously start moving because there's all this energy stored in the room. Instead, those joules went into internal energy, right? They went into heating up the floor and the air and your muscles and the back of the couch where you were touching and all that kind of stuff. So this is the nature of potential energy, right? Potential energy comes from conservative forces, right? And conservative forces, of course, are all forces, of course, are an exchange, an interaction between two objects, and that's where the potential energy is. It's in the bond between the two objects. And so since in that previous example, if you think about what was going on, as you lift the rock off the ground, gravity's doing negative work. And so that negative work means that the rock is losing energy, and those joules are conserved. Where do they go? They go into the potential energy. So that's the reason for the negative sign. Students find this negative sign here very confusing, right? It's because wherever, the work done by the conservative force, if it's positive, it means you're giving energy to the rock, right? So then you say, well, where did those joules come from? They came from the potential energy. So the potential energy between the rock and planet Earth needed to go down in order to supply those joules. The reverse, if you drop the rock and the rock falls, gravity's doing positive work, right? And so that means the rock is increasing its energy, which you see in the form of kinetic energy, right? So where did those joules come from? Well, they came from the bonding energy. They came from the potential energy stored in the system. And so it is a loss of the potential energy in order to do positive work, right? It comes from our definitions, right? The work is telling us the energy that's going into or out of the object. And when we're tracking potential energy, we're thinking about the work coming into or out of the relationship or the bond between the two objects in the system. And so that's why the negative sign is there, right? If the bond is losing the energy, then the object is gaining it and vice versa. Okay, so if we use this idea, what does the work energy theorem look like? Let me just give you a couple formulas here, right? So of the conservative forces, here are the two that we'll be using, right? So gravitational force. So what is the work done by gravity that is path independent when I lift it a distance delta h, right? So I start at h initial and I end at h final. I take the difference, hf minus hi, that's delta h. That is the displacement in the y direction, right? So that's the delta y that I get when I do the dot product of work and displacement. And the force due to gravity here, we're assuming we're staying very close to the surface of the Earth, and so we're going to use that the gravitational force is just the weight mg. Spring, of course, has the formula kx, and so you have to actually find the area under the curve because that's a function, right? It's not a constant force. And so when you find the area under the curve, it's a triangle, and you get this 1/2 kx squared. And so why do we have negative signs here? So in both cases, the negative sign comes from the fact that the displacement is in the opposite direction of the force, right? It's negative mg delta H, because if the delta H is positive, that means you're going upwards and gravity is downwards. So that's negative work done by gravity because the vectors are in opposite directions. Likewise, if you compress a spring or expand a spring, pull it out, the force is in the opposite direction of the displacement, right? So the force is in the opposite direction of the x. And so once again, that is negative work done by the spring. Right? You got to be careful about these because you may be pushing or pulling on the spring or lifting or dropping the rock, and you may be doing all kinds of different kinds of work, but we're looking specifically at the work done by gravity and the work done by the spring, not the total work or the work done by the person, all right? So if that's the negative of the potential energy, then we just, put a negative sign in front of there and the negative signs go away. And the gravitational potential energy, just assuming you set h sub I equal to 0, right? You got a gravitational potential energy function of mgh. That's assuming, well, once again, that we're close. There's a different universal gravitational potential energy that goes with universal gravity, right? So if you need to do g m1 m2 over r squared, it has its corresponding gravitational potential energy, which of course is also more complicated and looks more like g m1 2 over r squared. And then if you have any elastic media that's obeying Hooke's law, then you have an elastic potential energy of 1/2 kx squared. So these are basically the two types of potential energies. So even though I'm explaining everything in general, when it comes down to problem solving and the types of problems you can expect, really these are the only two conservative forces you need to be alert to right now, right? Is gravity and springs and elastic materials that obey Hooke's law. All the other common forces that we've been using in the course so far and that we'll continue using in this chapter are non-conservative forces, right? And so do not have a potential energy associated with them. Sorry, this is where I thought we were headed next, right? So if we take our work energy theorem, now we can divide up the network into these two different camps, right? So you could have forces that are conservative in there, and you might have forces that are non-conservative. You don't have to have both, but in general, right, a force will fall into one of those two camps. And so I'm just breaking the network here into those two terms. And of course, that's equal to the change in kinetic energy, which we talked about a little while ago. And now I'm going to substitute in for the work done by non-conservative forces. I'm going to say, well, I know where those joules are going, right? They're going into these potential energy bonds, right? And if I took work away by doing negative work, then the potential energy is going to increase, right? There's that negative sign again. So then I can you see where I'm going to head is I'm going to bring this potential energy over to the right-hand side. And here is the form of the work energy theorem that winds up getting us a step closer to seeing conservation of energy. And that is, instead of talking about the total work, let's do the work done by all the forces that aren't gravity, that aren't springs, that aren't electricity, right? All the non-conservative forces. The work done by those forces will total into going not just in the kinetic energy, but into the kinetic energy and the potential energy. And this, of course, seems more complicated, but the advantage is if you can determine that there are no non-conservative forces doing work, which if you go back and look at a lot of our problems, a lot of times we'll say ignore friction, or something like that. Or, we just have something sliding down a slide or something like that. Now, all of a sudden, if you can get rid of the work done by non-conservative forces, the left-hand side goes to 0, and you get a nice conservation law of the KE and the PE must total to the same number, right? The energy can be traded back and forth between the kinetic and potential energies all day long, but the total needs to be the same. And this gives us a very elegant way of solving a lot of problems that are much more complicated using kinematics and F equals ma. You can solve all kinds of problems that basically aren't solvable or extremely difficult to solve just using the equations of motion and Newton's second law. So here's what we've got, right? This is just a summary of the three major points. So the first bullet point, right? If you are not going to distinguish between your forces and just say, okay, everybody, let me count the work done by everybody, then I'll calculate the network, and that goes into changing the kinetic energy, right? If it's a negative network, the kinetic energy final will be lower than the initial, and if it's positive work done, then I'll have more kinetic energy final than I did initial, right? The more sophisticated thing here where we can think about potential energy and actually track where the joules are going, which gets us a step closer to kinetic energy, is to only consider the work done by the non-conservative forces, and that goes into changing the mechanical energy, which remember is just a shortcut for saying KE plus PE. And then if you are in a situation where there's no work done by non-conservative forces, then you have an isolated system and energy is conserved, and you get this nice kinetic energy and potential energy at any point in the system, add those numbers up, that total will be the same at any other point in the future or the past. And what's so great about this is this is a scalar equation, right? I mean, these are energy is a scalar, it has no direction. You've got simple formulas like 1/2 mv squared and mgh and 1/2 kx squared. These problems tend to be, very amenable to algebraic solutions. So let's just talk through a couple of examples, right? So if I'm dropping a rock, at the top before I let go, all the joules are in potential energy. Now, as it falls down towards the ground, instead of thinking about the work, the forces causing acceleration, let's just tell the story in terms of joules, right? The mgh, as h gets smaller and smaller, the gravitational potential energy is going to get lower and lower. So where do those joules go? Well, they go into kinetic energy, right? So every joule lost in mgh, the gravitational potential energy, goes into 1/2 mv squared and goes into speeding it up, right? So here's an alternate explanation, if you will. It's actually closer to the truth, right? This is really what's going on, is it's all about energy. It's not really about forces and accelerations. That is a way of describing it, but the advantage of the energy way of describing it is it's going to work in all systems all the time, even where forces are not well defined. And by the time that rock hits the ground, the h has gone to 0, which means there is no longer any mgh. So all the gravitational potential energy joules have been lost and converted into kinetic. If you look at the upper right over here, we got the same kind of story, but it's with a loaded, like a spring dart gun. So when you compress that spring and before it releases the dart, you have all this stored potential energy in the form of 1/2 kx squared. And then as that spring expands to its relaxed length and releases the dart, where does the 1/2 kx squared go? It goes into 1/2 mv squared. Right? And this would be a relatively harder problem to solve using just forces because the force is changing every single second. Right? This is a non-constant force. But energy doesn't care. We're just taking a snapshot at the beginning and saying all the joules are 1/2 kx squared, and a snapshot when it gets released and say all those joules have been turned into 1/2 mv squared. And we don't have to worry about the details, right? And here's another example where not worrying about the details is important, right? What if I asked you the following question, like Paul and Kathleen, they start at the same height. They're both going down water slides, so you can ignore the friction. They take these two different paths, and I ask you, how do their speeds compare at the bottom, right? Classic kind of physics question. Well, the inclined plane problem is really complicated here, right? Because the angles are changing all the time, and so the forces are changing all the time. But that key of ignoring friction means that I don't have any non-conservative forces that are doing any work, which means I can imply conservation of mechanical energy. And I can just say, look, Paul's mgh at the top all gets converted to Paul's 1/2 mv squared at the bottom. So Paul's energy initial is just mgh plus a 0, and at the bottom is 0 plus 1/2 mv squared. And so his mass cancels out, and I get that the speed at the bottom is something like the square root of 2gh, right? And if I do the same analysis with Kathleen, I get the same answer. And it turns out, it doesn't matter what path you take, they're all going to come off the bottom with the same speed. Now, sometimes it doesn't sit well with people because people will say, oh, but they don't spend the same amount of time in here. And that's true. They spend different amounts of time at different areas along the slide. But if you do a photo finish of each one as they cross the bottom, you will find they're traveling at the same speed. Okay, one final thing, and then I'll wrap it up. This is a pretty heavy lecture here. The third form of energy that we're going to ignore most of the time. I don't want you to, although our calculations are not going to try to track these joules, and we may be sloppy in our language and say things like, oh, the joules are lost, right? What we really mean is they're lost in mechanical energy. You don't find them in KE or PE. Like this is the kind of thing that friction is always doing to us, right? But let's be careful about this. Those joules are still out there, right? They've just been translated. It's not in the speed of the crate across the floor as friction slows it anymore. It went into heating up the surface of the floor and the bottom of the crate and the air in the room and maybe generating the sound and stuff like that, right? So it goes into these other places. But if you could find all those joules of energy and track them down, you would find that the total is still conserved. As a practical matter, though, it's very hard to find those joules, and you're not going to be able to take that unorganized energy that went into all these microscopic forms and easily harness them all up and shove them back into the block and get it going again, right? Which is why it's so different from potential energy, where Richard Feynman would say that kinetic energy and potential energy, the mechanical energies, are organized energies, right? and that the internal energies are disorganized energies, right? The joules are there, but they're not sort of available for you to extract and do good work with. I mean, obviously you can build heat devices and heat pumps, but you're not going to get all the joules back. Okay, that is plenty for today. Thanks for hanging in there with me.